morning friends. We shall continue our discussions on Laplace transform. Yesterday we derived the transforms of some standard functions. We will continue with that. Before we go to the set of other properties, I just like to mention that a function f t is Laplace transformable if f t mod e to the power minus sigma t dt 0 to infinity is a finite quantity, that is it is less than infinity. Now, if you have a function say f t equal to say t squared or t cubed, will this property hold good for this f t? Let us see. F t into e to the power minus sigma t as t tends to infinity, how much is this product? T cubed into e to the power minus sigma t, okay, limit t tending to infinity. So, what will be the limit? I can always write this as e to the power sigma t, I can write as 1 by e to the power sigma t. So, 1 plus sigma t, 1 minus 1 plus sigma t plus sigma squared t squared by factorial 2 and so on, and the t cubed on the numerator can be brought back here, it can be brought down here. So, this will be 1 by limit t tending to infinity 1 by t cubed plus sigma by t squared plus sigma squared by factorial 2 t, all right, like that, plus sigma cubed by factorial 3 t cubed will get cancelled, and after that you will get sigma 4 by factorial 4 t and so on. Okay. Now, how much is this coming to? One by t cubed, it will be 0, this will be 0, this will be 0, this will be finite. So, it will be equal to 1 by sigma cubed by factorial 3 plus this will be infinite terms multiplied by t. So, it will be equal to 0, this is limit t tending to infinity. So, this will be 0. So, a function now when t tends to 0, this is infinity, this is infinity, this is infinity, these are all zeros. So, 1 by infinity, that is again 0. So, what will this function look like? T cubed is a function which is going up like this, cubic parabola, all right, and t cubed into e to the power minus sigma t, e to the power minus sigma t is a function going like this. So, the product will be starting from 0 ending at 0. So, somewhere it may have a peak and then it will be going like this. So, the area will be finite, this is going to 0. So, area is finite. So, I have just taken an example with t cubed. It can be shown that for any t to the power n, it will be always converging to a finite value, and hence the integration from 0 to infinity will also give you some finite sum, it will be less than infinity. So, it is transformable. Functions of this kind, so e to the power minus or plus a t squared, if f t is of this kind, then you will find again by taking the limits this will not tend to a finite value. So, this is not transformable, but any other functions at t to the power n or functions of this kind, they will be transformable. So, for any transformable functions you have to check whether this property holds good or not. F t may go to infinity, but f t into e to the power minus sigma t, this integration, this entire product, if it goes to a finite value, then and the integration if it gives you a finite value, then it is transferable. Next we will take up some properties of Laplace transform. So, Laplace transform of a shifted function. last time we discussed about some shifted functions, how to represent them. Suppose f t is a function like this, then f t minus tau into u t minus tau is basically the same function starting after an interval tau. Okay. So, what will be the Laplace transform of this in terms of Laplace transform of this function? Okay. What will be the Laplace transform of this function in terms of the Laplace transform of this function? We would like to find out that. Now, Laplace transform of f t minus tau u t minus tau will be equal to integration 0 to infinity f t minus tau u t minus tau e to the power minus s t dt, okay, by definition. So, that gives me equal to 0 to infinity. Now, between 0 and infinity, if I take a function, now the function starts after tau, that means it is 0 here. So, the integration from 0 to infinity means tau to infinity. So, I can break it up into 0 to tau f t minus tau u t minus tau e to the power minus s t dt plus tau to infinity f t minus tau u t minus tau e to the power minus s t dt, and this part is 0 to tau. So, it is equal to 0 plus tau to infinity t minus tau u t minus tau e to the power minus s t dt. Now, t minus tau I can put another variable t1. So, dt is equal to dt1 and t is equal to t1 plus tau. So, replace t by t1 plus tau. So, when t is tau, t1 is 0. So, this limit becomes 0 to infinity f t1 u t1, actually f t1 u t1 from 0 it does not mean much. Here I can break it up into e to the power minus s t1 e to the power minus s tau. E to the power minus s tau can be taken out because the integration is with respect to t1. So, thank you very much. 0 to infinity f t1 u t1 e to the power minus s t1 dt1, and what is this? F of s. So, in terms of the original transform, the shifted function has a transform, that is e to the power minus s tau into f s. Okay. So, now let us derive some of those, the Laplace transform of some of the shifted functions we discussed yesterday. Let us take a simple example. Suppose this is a t, this we wrote as equal to a function like this plus function like this minus a and plus a, is it not? So, what will be the Laplace transform of the first function? A by s, this one a by s shifted by t. So, multiplied by e to the power minus s t. Just now we have seen that any function if it is shifted by tau, so the original Laplace transform multiplied by e to the power minus s tau, this will be the result. So, this is a by s into 1 minus e to the power minus s t. Okay. Now, suppose we take t very small, tending to 0 and a is tending to infinity, such that a into t is 1. we get a unit impulse, is it not, when t tends to 0 and a tends to infinity, but the product is finite, and in this case if it is 1, then what will be this? This will tend to, for this f t is nothing but delta t. Okay. So, this was our f t. So, Laplace transform of delta t we want to compute, we will substitute that condition here, a by s into 1 minus, what is e to the power minus s t? 1 minus s t plus s square t squared by factorial 2 and so on. Okay. Now, let me simplify here itself. 1 will go a by s into s into t, then you will find 1 s will go s t squared and so on. Okay. A by s, s t minus s squared t squared by factorial 2 and so on. So, that gives me equal to a t minus sorry a s t squared by factorial 2 plus a s squared t cubed by factorial 3 and so on. And this a t is 1 and this is a t into t, t tends to 0 means this will be all 0. Okay. T tends to 0. So, Laplace transform of delta t is unity. Okay. What would be the Laplace transform of a periodic function? So, let us take periodic function like this and so on. So, this is of magnitude 10, this is 1, 2, 3, 4 and so on. So, let us take first of all the first block which is repeated after every period. So, what is the Laplace transform of this first block? Could you please tell me? This will be 10 by s into 1 minus e to the power minus 1 s, is it not? Tau is 1. Let us call it f1 s. Then what will be fs? The same thing being repeated. So, it will be f1 s plus f1 s is repeated after 2 seconds. So, f1 s into e to the power minus 2 s plus f1 s into e to the power minus 4 s and so on up to infinity. Okay. So, f1 s if I take common, it will be 1 plus e to the power minus 2 s plus e to the power minus 4 s and so on, which means f1 s into, it is a geometric series, common ratio is e to the power minus 2 s. So, 1 minus e to the power minus 2 s. Now, f1 s is already obtained, substitute that, what do you get? f1 s equal to already known. So, I am just repeating it here. Therefore, Fs will be 10 by s 1 minus e to the power minus s 1 minus e to the power minus 2s. Okay, e to the power 1 minus es goes out. Is that all right? Let us take another example. A periodic function, once again like this. This is 10, this is minus 10. Okay, 1, 2, 3, 4 and so on. What would be the Laplace transform of this function? Can you write in one go? What is this? F1s is, see, if it is the same block being repeated with alternate signs, then there is no problem. I can take this as the primary block, first initial block, whose Laplace transform is already known. Then what will be Fs? It will be F1s into 1, then minus e to the power, it is shifted by 1 second and then its sign is changed. So, e to the power minus s plus e to the power minus 2s minus e to the power minus 3s plus e to the power minus 4s and so on. Is that all right? So, how much is this? Common ratio is now minus e to the power minus s. So, it will be F1s by 1 plus e to the power minus s. So, that is 10 by s 1 minus e to the power minus s by 1 plus e to the power minus s. Very familiar form, no? What is it? Can I not take e to the power s by 2, multiply throughout by e to the power s by 2. So, it will become e to the power s by 2 minus e to the power minus s by 2 divided by e to the power s by 2 plus e to the power minus s by 2. So, this will be not 2j, why j? I am not putting j omega and all that. This is simply cos, this is sine or sine and cos. So, it will be tan. So, it will be 10 by s tan hyperbolic s by 2. Okay. Another example, if I have a pulse train, zero, 2, 4, 6 and so on. This is delta t, this is delta t minus 2 and so on. So, what will be Fs for this? For the first one it is 1, for the next one it is 1 into e to the power minus 2s plus e to the power minus 4s and so on. So, it will be 1 by 1 minus e to the power minus 2s. Is that all right? If you have alternately coming, say plus 1 minus 1, delta t minus delta t plus delta t minus delta t with shifts, then only change will be here. Okay, plus. Very good. Now, we have another important property. Suppose Laplace transform of f t is given as f s. What will be the Laplace transform of f dash t, where f dash denotes the first derivative? What will it be? So, by definition, this will be 0 to infinity d dt f t e to the power minus s t dt. So, if you integrate by parts, all right, this you can take as integration of u dash to v is u v minus integration u v dashed. Okay. So, if I take this as v, okay, this can be differentiated, this can be integrated. So, it will be f t, if I integrate this into v e to the power minus s t 0 to infinity minus derivative of this will become minus s into e to the power minus s t, and integration of this is f t dt. So, this one will give me, if I put infinity, this becomes 0 minus, if I put 0, it will be minus f 0, minus and minus will make it plus, and integration of f t e to the power minus s t dt is f s. So, it is s into f s, where f s is the Laplace transform of original function f t minus f at 0. Okay. Now, we shall derive the Laplace transform of integrals of functions from here. You can go from the basic definitions. There is another way of looking at it. Let us take f t as some f 0 t df t by dt as d f 0 by dt as some f 1 t. Therefore, d square f t by dt squared is d f 1 t by dt as f 2 t. Okay. So, f 0 t, f 1 t, f 2 t means they are all successive derivatives, and corresponding Laplace transforms we denote as capital F 0 s, f 1 s, f 2 s, and so on. So, just now we have derived f 1 s is what? Derivative f 1 t, its Laplace transform is f 1 s. So, it will be in terms of f naught s, f naught s minus f naught f 0 at 0. Is that all right? Similarly, f 2 s will be s into f 1 s minus f 1 at 0. If I substitute f 1 s here, it will be s square f naught s minus s minus f 1 0. That means, if I take the nth derivative and its Laplace transform will be in terms of the original Laplace transform s to the power n, sorry, this is n, minus s to the power n minus 1 f naught naught minus s to the power n minus 2 f 1 0 and so on minus s to the power 0 when I am calculating f n, then f n minus 1 0. Okay. This is just by induction. We have gone downward from f 0, derivative is f 1, next derivative is f 2, etc. If we go up, it will be integration. All right. So, these equations can be just a little bit of manipulation. I can write on this side f 1 s is s f naught. So, f naught s is how much in terms of f 1? It will be f 1 s by s plus f naught naught by s. Okay. So, sorry, if you are given the Laplace transform of f1, in terms of that is f1t is known, in terms of that can you compute the Laplace transform of its higher order function? By higher order I mean the integral, lower order means derivatives. So, f naught s, that is the integral of f1t, what will be its Laplace transform? So, f naught s will be the Laplace transform of the original function divided by s now, plus what is f naught naught? The integral evaluated at t equal to 0. What does it mean? So, it is like this. If you have a current expression, for example, current is, for example, in a capacitor, 1 by c integral I dt 0 to t is the voltage at any instant. If I have to take the Laplace transform of this, given the Laplace transform of it as is, what will be Vs? Vs is integral of I, is it not? So, if I have to compute Vs, it will be 1 by c into integral of, this means original Laplace transform divided by s, then plus what? Is it I0? What is f0? It is integral of that. So, integral of I dt, okay, divided by s, and this is to be evaluated at 0. From where do we start? So, 0 minus to 0 plus, or basically whatever has been there before the counting of time, before t equal to 0. So, that gives me integral of I dt is what? Charge q, is it not? So, integral I dt means this is to be evaluated at t equal to 0, means the initial charge q naught, all right. Mind you, it is not initial value of I, initial value of integration of I. When you take the integration, so initial value of not f1, f naught means integration of f1, all right. If the initial condition is given as 0, then there is no problem. So, 1 by Cs into Is plus, if I call it Q naught by Cs, Q naught by C is nothing but initial voltage across the capacitor. So, V naught by S. Okay. So, when we evaluate, for example, when we evaluate the voltage across a capacitor, you are energizing by this, there can be a resistance also, you want to measure the voltage across this capacitor, then its initial voltage plus at any instant, if current is IT, if you want to deal with this problem in the Laplace domain, then Is into 1 by Cs, this total sum will be the voltage across the capacitor. Initial voltage across the capacitor plus the drop due to this is the total voltage at any instant. Now, we will take up one or two small examples, then again we will come to some other properties. What will be Laplace inverse of say 1 by s into s squared plus omega squared? 1 by a squared plus omega squared, what is the Laplace inverse? If you remember, this is sin omega t. What is the Laplace transform of sin omega t? Omega by a square plus omega square. So omega is not there, so I will just write sin omega t by omega. Okay. And just now we have seen, if the initial conditions are not given, otherwise mentioned, say it will be treated as 0. So what will be therefore Laplace inverse of 1 by s into s square plus omega square? 1 by s into s square plus omega square. It will be integration 0 to t sin omega t by omega dt, is it not? So that will give me 1 minus cos omega t by omega. Okay. 1 comes because you are putting limit on sin cosine omega t. So this, there is another omega, so while integrating you will get omega squared, sin omega t will give me another omega. So 1 by omega square 1 minus cos omega t. Is that okay? One may do it by partial fractions. I can write this as a by s plus bs by a square plus omega square. Let us see how much is a. Multiply by s, put s equal to 0, it will be 1 by omega squared. How much is b? Multiply by s square plus omega square, divide by s, so it will be, and then put s square plus omega square equal to 0. So if I multiply by s square plus omega squared, this will go on the left hand side, it will be 1 by s, then this will be s square plus omega square in the numerator, and here it will be bs, and then if I divide by s, this will be s square, this will be s square, so it will be 1 by s square on this side it will be a into s square plus omega square plus b, and now I am making s square plus omega square equal to 0. So that means 1 by minus 1 by omega square, alright, that will be b. So this one will be 1 by omega squared into 1 by s minus b means 1 by omega square. So s by s square plus omega square. Again, if you take the Laplace inverse, you will get the same result. So you can do it by either method, alright, making use of the property of integrating a function or making partial fractions. Similarly, you can solve for 1 by s square into s square plus omega square. So if you know the result of this, once again divide by s means once again an integral function. So you integrate this one again, you will get the Laplace transform. Partial fraction will be simpler, is it not? It will be 1 by s square minus 1 by s square plus omega square. So that will give me s square plus omega square minus s square. So I will divide by omega squared. So corresponding inverse will be 1 by s square is Laplace transform of what? Ramp function t into ut, okay, and this one 1 by s square plus omega square sin omega t by omega. So it will be 1 by omega square t ut minus 1 by omega cube sin omega t. Okay. I did not write ut all the time. I told you if you write t, so so long as you understand it, it is a ramp function, it is okay. Another important property we will derive now. See, by definition we have f t e to the power minus s t dt. The common term is s, common variable is s. If I differentiate with respect to s, what do we get? If you differentiate with respect to s, it will be t into e to the power minus s t with a negative sign, f t dt. And what is this? Laplace transform of t f t with a negative sign. So, Laplace transform of t into f t is minus dfs by ds. Okay, minus dfs by ds. Again we will take a few examples. What will be Laplace inverse of this? 1 by s squared plus b squared. If I take the derivative with respect to s, what is it? Derivative of this 1 by s squared plus beta squared. Yes, could you please tell me? 2s minus 2s. Okay. So, if I put a beta here, all right, therefore t into this is corresponding to sin beta t, is it not? T into sin beta t, t into sin beta t, Laplace transform of t into sin beta t is how much then? T into sin beta t, t into f t is dfs by ds with a negative sign, all right. So, this is corresponding to sin beta t. So, t into sin beta t should be equal to derivative of this with respect to with a negative sign. So, derivative is this. So, this is nothing but 2 beta s by s square plus beta square whole square, is it not? Is that all right? T into cosine beta t, what will be the Laplace transform? Cosine beta t is s by s square plus beta square. If you take the derivative of this, how much is it? So, dds of with a negative sign, dds of s by s square plus beta square. How much is that? And dds of s by s square plus beta square, s square plus beta squared
minus 2s square
into derivative of this minus 2s squared divided by s square plus beta square whole squared. So, that gives me s squared minus beta squared divided by s square plus beta square whole square. Okay. The other one is t into sin beta t, 2 beta s by s square plus beta square whole square. Okay. So, I can make any combination t into cosine beta t plus minus t into sin beta t. Laplace transform of this will be a squared minus beta square by a square plus beta square whole square plus minus 2 beta s by a square plus beta square whole square. Okay. Now, you already know beta by a square plus beta square corresponds to sin beta t, and this one corresponds to cos beta t. So, by making manipulations there are 4 results now, one is this plus this minus this. So, I have already got 4 such Laplace transforms. By manipulating you can find out the Laplace transform of this, because I have to break it up into, say if I make partial fractions or manipulate these, I can get the inverse of this. I leave it as an exercise, this do it yourself. Okay. It is not very difficult. Next we take up application of Laplace transform in simple network problems. Suppose we consider a simple RL circuit. There is a DC source of voltage V and the switch is put on at t equal to 0. Initially this is uncharged. What would be the expression for the current IT? We write V, you are suddenly switching on, so it will be V u t. V is the magnitude of voltage, you are applying a step voltage, and if I is the current, then it is R I. I am not writing I t, it is understood I is a time varying quantity, L di by dt. If I take Laplace transform on both sides, it will be V by S, on this side it will be R I S plus L di by dt, and what is the Laplace transform of the derivative function? S times I S minus I 0. If I assume the initial condition to be 0, then I 0 is 0, so that will not come. So, it is R plus S L into I S. Alright. So, like you are having voltage equal to impedance into current in simple AC circuit, here also the applied voltage in the transform domain, this is equal to R plus S L into current in the time domain, Laplace domain. So, in the transform domain, I will write V naught, excuse me, V naught means a specific value, and V s is the Laplace transform of V t. In this case it is V 0 into u t. Okay. So, V s by I s, that means in the transform domain voltage function by current function is equal to R plus S L in the transform domain. So, a resistance, therefore, this circuit I will write as V s as a voltage source and an impedance which is R plus S L, and the current is I s. So, an impedance is given by R plus S L for R and L. In a similar manner, we can show if there is a capacitance, if there is a voltage source here V t Ri plus 1 by C integral I dt is equal to the applied voltage. If I take the Laplace transform, it will be R into Is plus 1 over C into S into Is. Once again, if I assume the capacitor to be initially uncharged, then that Q naught by Cs will be 0. So, this side it will be Vs, or Vs by Is will turn out to be R plus 1 by Cs. So, if it is an inductive element, it will be R plus SL. If there is a capacitive element present here, then it will be equivalently represented by 1 by SC. So, if you have R, L, C, wherever there are resistances, you replace it by, you retain it, that is resistance will be retained as it is, inductance will be replaced by SL, capacitance will be replaced by 1 by SC, and in all network configurations henceforth we will be using the transform domain variables R, SL, 1 by SC. Sorry. If we do this, then any network problem can be solved. Let us take 1 or 2 more examples. You have a source here, a resistance here, okay. Therefore, we shall replace this entire circuit by an equivalent V1S R1 you can show it like this, or a symbol like this can also be used for a generalized impedance ZS. It can be R, it can be 1 by SL, 1 by SC, it can be SL, or any combinations. So, this is R2 plus SL2. Similarly, this one is R3 plus 1 by SC3, and this side you have got V2S. Now, for calculating the current through any branch or potential at any node, you can apply superposition theorem, nodal analysis, Thevenin's theorem, any theorem you want, by treating these as simple algebraic operational impedances, alright, treating S as an algebraic operator and treat this as it is, and then when you get the expression for current Is, take the inverse, you get the current It. So, if I am interested in the current through this I2S, what will be I2S? You can go for nodal analysis. So, let this potential be VA. So, VA minus V1S by R1 plus VA by R2 plus SL2 plus VA minus V2S by R3 plus 1 by SC3 equal to 0. Now, V1S and V2S will be given to you. It may be a step function, ramp function, or any other function. So, put those values, solve for VA. VA means VAS. Okay. once you know VAS, then VAS divided by R2 plus SL2, therefore I2S will be VAS by R2 plus SL2. Okay. So far you have got the solution in terms of S. Now you make partial fractions, expand it partial fractions, and then take the inverse, you will get the current I2. Okay. While making partial fractions, sometimes you may come across multiple poles at a particular point. Say we want to find out the partial fractions of, say the denominator is s plus alpha 1 into s plus alpha 2 and so on, but s plus some alpha k is having n number of roots, that is 3, 4 multiple roots. Then this can be written as a1 by s plus alpha 1 plus a2 by s plus alpha 2 and so on. Evaluation of a1, a2 etc. is very simple, straightforward. Multiply by s plus alpha 1, then make s plus alpha 1 equal to 0, you will get a1 and so on. But this one will be some ak1 by s plus alpha k n plus ak2 by s plus alpha k n minus 1 and so on. Evaluation of this becomes a little difficult. Straightforward, if you apply that technique, then you will be able to get only ak1. So for evaluation of ak1, you multiply by s plus alpha k to the power n both sides. So fs is multiplied by this and then put s equal to minus alpha k. Okay. This product, let me call it sum qs, evaluate at minus alpha k. Then ak2 will be derivative of this qs and then evaluate at s equal to minus alpha k. Similarly, ak3 will be 1 by factorial 2 d square qs by ds square, second derivative you take and then substitute s equal to minus alpha k and so on. Third derivative it will be factorial 3 and so on. So you keep on taking the derivatives of this product and then evaluate the function at s equal to minus alpha k, that will give you successive residues. Once you know that, you can expand, you can find out the inverse. Okay. So we will stop here for today. Thank you very much. You try some of the problems at home and we will take up some numerical problems in the next class. Okay, good afternoon friends. We will continue with Laplace transform. Today we will have some tutorial session. We will be solving some problems employing Laplace transform. Let us take simple functions. What will be the Laplace transform of 1 by 2 s squared sin at minus sin at? What will be the Laplace transform of this? So this one can be written as 1 by 2 s square. What is sin hyperbolic at? E to the power at minus e to the power minus at divided by 2 minus sin at. So, it is pretty simple, 1 by 4a squared e to the power at will be 1 by s minus a minus 1 by s plus a, is that all right, minus 1 by 2s squared sin at will give you a divided by s squared plus a squared, is that okay. So, if I add these two, it will be s plus a minus s plus a, so twice a, so that will be 1 by 2a into a squared minus a squared minus here 1 a goes, so 1 by 2a to 1 by a squared plus a squared. So, 1 by 2a I can take out, it will become 1 by a squared minus a squared minus 1 by a squared plus a squared, and that gives me a squared plus a squared minus a squared. So, twice a squared, so twice a will go, so a by s to the power 4 minus a to the power 4, okay, plus 2 times ys is equal to 5 by s. So, it is s squared plus 3s plus 2 into ys, which is 5 by s. So, how much is ys? 5 divided by s into s square plus 3s plus 2 can be written as s plus 1 into s plus 2. Okay. I can write it as a by s plus b by s plus 1 plus c by s plus 2, and taking the inverse of these three, I will get the final yt as a into ut plus b into e to the power minus t plus c into e to the power minus 2t, where a, b, c residues can be calculated from here by standard partial fraction technique. Okay. So, we will stop here for today, we will take it up in the next class with further examples using Laplace transform for network problems. Thank you very much.